Hello and welcome to Sleepy Engineering. In this video, we will explore the complete history, structure, and function of one of the most powerful machines in rail transport, the diesel locomotive. This narration is intentionally slow, detailed, and repetitive. It is designed to help you relax, to help you focus, or to help you fall asleep. There will be no sudden sounds, no music, and no emotional tone, only the steady voice of information. Now please sit back, close your eyes if you wish, and let the story of the diesel locomotive begin. A diesel locomotive is one of the most recognizable and enduring machines in the history of rail transportation, and to understand its place in engineering, we must begin with a calm and careful overview of what defines it and why it became such a central part of the railway world for more than a century. Because unlike steam locomotives, which relied on boilers filled with water, heated by burning coal or oil, a diesel locomotive draws its power from the controlled combustion of diesel fuel inside a heavy internal combustion engine, which in turn produces the mechanical or electrical energy needed to move the wheels along the tracks. And although the phrase diesel locomotive might sound simple, in reality, it describes an entire family of machines that can vary widely in size, design, purpose, and technical configuration. Yet they all share the same fundamental principle of turning chemical energy stored in fuel into the mechanical energy required to move thousands of tons of cargo or hundreds of passengers across vast distances in a reliable and efficient manner. And this principle has made diesel locomotives not only a practical tool of industry, but also a symbol of modern progress in rail transport since the early 20th century, when the first experimental models began to appear. Engineers and railway operators quickly realized that the diesel engine offered certain advantages that steam could never fully match, including higher efficiency, lower operating costs, greater range, and less dependence on complex water supplies and maintenance facilities. But before diving into the details of components and subsystems, it is important to slowly and clearly establish what exactly a diesel locomotive is and how it is organized at its most basic level. A diesel locomotive is a self-contained rail vehicle that carries its own prime mover, meaning the large diesel engine located within the body of the locomotive. This engine burns diesel fuel and delivers power either directly through a mechanical transmission, through a hydraulic transmission, or most commonly through an electrical transmission system, where the diesel engine drives a generator or alternator, which then produces electricity that powers traction motors connected to the wheels. This configuration is known as the diesel electric locomotive, and it has become the standard design used in nearly every part of the world today, because it combines the advantages of diesel power with the flexibility of electric drive. But the significance of diesel locomotives cannot be fully understood only by describing how they operate, because their importance also lies in the way they transformed railway operations by eliminating the long delays required to raise steam, by reducing the size of support crews, and by allowing trains to start and stop much more quickly than with earlier designs. The arrival of diesel locomotives represented a technological turning point for railways. And while steam locomotives held a certain romantic image of smoke and fire, the diesel locomotive represented a new age of rationality and industrial precision, where reliability and efficiency took precedence over spectacle. And in this sense, the introduction of diesel locomotives mirrors many broader themes in the history of engineering where older systems built on visible energy were gradually replaced by newer systems built on hidden, but more controlled forms of energy. And as we listen carefully to this story, it becomes clear that the diesel locomotive is not simply a piece of machinery, but a carefully balanced collection of interacting systems, each designed to work in harmony under heavy stress and constant use. The body of the locomotive provides structural strength and houses the components. The prime mover provides the energy. The transmission system channels that energy to the wheels. The fuel system delivers the diesel fuel. The cooling system prevents overheating, and the control systems allow the driver to manage all of these elements safely and predictably together. These parts form one of the most important vehicles in modern transportation history, a vehicle that has carried coal grain, steel oil, passengers, and countless other goods across continents for decades. And even now, as new technologies emerge, and as electric locomotives and alternative fuels gain attention, the diesel locomotive remains present in many parts of the world, where its combination of independence, durability, and efficiency ensures that it will not be replaced quickly. The introduction to diesel locomotives must therefore be understood not only as a description of how a machine functions, but also as a reflection of why this machine has endured for so long in practical service, and why it continues to inspire engineers, historians, and railway enthusiasts alike. Because the story of the diesel locomotive is not just about pistons, cylinders, and motors, but also about how human societies adapt technologies to fit their needs, and how certain designs, once introduced, achieve such balance and effectiveness that they remain central for generations. When you imagine the form of a diesel locomotive, you might picture a long rectangular body with rounded or angular edges resting on two heavy bogies, each carrying multiple axles and wheels. On top of this massive body sits the cab, where the driver commands the machine, and inside the body lie the engine, the alternator, the cooling radiators, the fuel tanks, the compressors, and the miles of wiring pipes and connections that make it all work. And although these details will be explained carefully in the following sections, it is important at the very beginning to visualize the diesel locomotive as a whole system designed with precision to perform one fundamental task, which is to move trains consistently over long distances with as little disruption as possible. And so this introduction gently prepares us for the deeper exploration that will follow, where we will examine the components, the variations, the history, and the future of diesel locomotives in a steady and detailed way, designed to give you both knowledge and relaxation as you follow along with the slow unfolding of this story. In order to understand why diesel locomotives became such an essential part of railway history, it is necessary to look carefully at the transition period between steam power and diesel power, because this change did not happen overnight, but rather unfolded slowly over several decades and was influenced by many technical, economic, and social factors. At the beginning of the 20th century, railways across the world were still dominated by steam locomotives, which had proven themselves reliable and powerful for almost a century. Steam engines were capable of hauling heavy loads, and their construction was well understood, but they required enormous amounts of coal and water, which meant that railways needed to build and maintain extensive infrastructure such as coaling stations, water towers, and maintenance depots. The process of heating a boiler also took hours, which reduced operational flexibility and made timetables less efficient, As industrial economies expanded and demands on transport increased, engineers searched for alternatives. The diesel engine invented by Rudolf Diesel in the late 19th century was already being used in ships and industry, and it soon attracted attention from railway designers because it promised higher efficiency, quicker start-up times, and lower operating costs compared to steam. Early diesel locomotives appeared in the 1910s and 1920s, but the technology was still developing, and many railway companies were cautious because steam was deeply established and supported by an entire supply network. However, the advantages of diesel could not be ignored. Diesel locomotives did not need frequent water stops. They produced less smoke. They required smaller crews, and they consumed fuel more efficiently. During the 1930s, several pioneering railways began introducing diesel locomotives, especially for passenger services, where speed reliability and reduced emissions were important in the United States. Streamlined trains, such as the Burlington Zephyr, captured public attention and showed what modern rail travel could look like. In Europe, Germany, France, and other countries began experimenting with their own designs. But the breakthrough came after the Second World War, when economies were rebuilding and efficiency became critical. At this time, diesel technology had matured and petroleum fuels were abundant, making diesel economically attractive compared to coal. Railway companies discovered that switching to diesel allowed them to reduce maintenance costs, labor requirements, and turnaround times. Diesel locomotives could also be linked together in multiple unit formations and controlled from one cab, which provided flexibility for freight and passenger services alike. By the 1950s and 1960s, countries such as the United States and the United Kingdom had almost completely replaced steam with diesel, while other regions, including parts of Asia, continued to rely on steam for longer because of local conditions. The transition was not only technological, but cultural, because steam locomotives had become symbols of progress. Yet despite their iconic image, their inefficiency and high costs made them obsolete. The diesel locomotive emerged as the practical answer to the needs of the modern railway, balancing power, reliability, and economy in a way that steam could no longer match. And so the mid-20th century stands as the great turning point, when diesel power reshaped the railway landscape and set the stage for the systems we know today. To understand the functioning of a diesel locomotive, it is necessary to look at the fundamental principles of the diesel engine, because this machine is the prime mover that transforms fuel into usable power. And without it, the locomotive is nothing more than a shell. The diesel engine belongs to the family of internal combustion engines, which means that the combustion process occurs directly inside the cylinders, rather than externally in a boiler, as it did with steam. Locomotives. The key principle of the diesel engine is compression, ignition. Air is drawn into a cylinder and compressed by a piston to a very high pressure, which raises the temperature to a point where diesel fuel injected at the end of compression ignites spontaneously. The explosion forces the piston downward, turning the linear motion into rotational motion through the crankshaft. This process is repeated in every cylinder, many times per second, producing a steady flow of mechanical energy. Diesel engines in locomotives typically have large numbers of cylinders, often arranged in a V or inline configuration, with 12, 16, or even 20 cylinders, depending on the power requirements. Each cylinder contributes to the overall output, and their movements are timed to maintain balance and reduce vibration. The power generated is either transferred mechanically, hydraulically, or most commonly through an alternator that produces electricity, which then powers traction motors connected to the wheels. This arrangement, known as the diesel-electric system, is today the dominant form used worldwide. One of the most important principles of diesel engines is their high compression ratio, which is significantly greater than that of gasoline engines. This high compression is what allows spontaneous ignition of the fuel-air mixture and also contributes to the efficiency of the engine, because more energy can be extracted from the same amount of fuel. Diesel engines are therefore known for their fuel economy and long range. In addition, diesel fuel itself has a higher energy density than gasoline, which increases efficiency. Further, another defining characteristic of diesel engines is their torque output. Unlike gasoline engines, which reach peak power at high speeds, diesel engines generate strong torque at low revolutions per minute. This property makes them ideal for locomotives because trains require immense pulling power, especially when starting from rest or climbing gradients. The ability to deliver heavy force at low speeds is precisely what allows locomotives to move thousands of tons with steady reliability. The diesel engine operates on the four-stroke cycle, which consists of intake compression power and exhaust during intake. The piston moves downward, drawing in air during compression. The piston moves upward, compressing the air to extreme pressures. Fuel is then injected at the end of compression and ignites, producing the power stroke that forces the piston down. Finally, during the exhaust stroke, the piston rises again, pushing burnt gases out through the exhaust valves. This cycle repeats continuously across all cylinders, creating the rhythm of the engine. Supporting systems are essential for maintaining this process. The fuel injection system must deliver fuel at the right time and pressure. The air intake must supply enough oxygen for combustion. The exhaust system must expel waste gases. The cooling system must remove excess heat, and the lubrication system must minimize friction and wear. Without these supporting elements, the diesel engine could not function for the long hours and heavy loads required. In railway service, locomotive engines are designed for durability. They use reinforced cylinder walls, heavy crankshafts, and robust bearings to withstand enormous pressures and stresses. They are also designed for continuous operation, sometimes running for days at a time without shutdowns. This durability, combined with their efficiency, explains why diesel engines became the dominant choice for railway traction, and why they continue to be used even today, despite the rise of electric systems. When we summarize the principles of diesel engines, we see four central qualities: compression, ignition, fuel, efficiency, high torque at low speeds, and durability. These qualities together create a prime mover capable of powering the vast and heavy trains that define modern rail transport. And it is through these principles that the diesel locomotive achieves its remarkable ability to move goods and passengers steadily across continents. Diesel locomotives may all share the same prime mover in the form of a diesel engine, but the way in which the power from that engine is transmitted to the wheels can vary, and this variation creates three main types of diesel locomotives, known as diesel mechanical, diesel hydraulic, and diesel electric. Each type represents a different engineering approach to the challenge of turning the rotation of the engine crankshaft into the rotation of the steel wheels on the track, and each type has its advantages and limitations, depending on the context in which the locomotive is used. The diesel mechanical locomotive is the simplest of the three, because in this configuration, the diesel engine is connected directly to the wheels through a mechanical transmission system, which usually involves a gearbox and drive shafts, just as in an automobile. When the engine rotates, it transmits torque through gears and clutches that adjust speed and power before delivering it to the axles. Diesel mechanical locomotives are generally limited to low power ratings because the size of gearboxes required for very high horsepower engines would become impractical. As a result, they are most commonly used in shunting yards, industrial plants, or on light branch lines where short trains and frequent maneuvering require only moderate pulling power. Their simplicity makes them inexpensive and relatively easy to maintain, but they cannot handle the massive loads required on mainline services. The second category is the diesel hydraulic locomotive. In this type, the power from the engine is transmitted through a hydraulic system using fluid couplings or torque converters instead of a mechanical gearbox. When the engine turns, it drives a pump that forces fluid through turbines, which then rotate. The drive shafts connected to the wheels. The advantage of hydraulic transmission is that it allows smoother power delivery and avoids the need for extremely complex gear systems. It also enables relatively high power outputs in a compact form, which made diesel hydraulic locomotives popular in countries like Germany. During the mid-20th century, German manufacturers such as Krauss-Maffei produced famous classes of diesel hydraulic locomotives that were used both domestically and exported to other nations. The United States experimented with diesel hydraulics as well, but they never became as widespread there because maintenance and efficiency concerns eventually limited their appeal. Nonetheless, hydraulic systems proved effective for certain applications, particularly where quick acceleration and good power-to-weight ratios were desirable. The third, and by far the most widespread type, is the diesel-electric locomotive. In this system, the diesel engine is not mechanically connected to the wheels at all. Instead, it drives a generator or alternator which produces electricity. This electrical energy is then fed to traction motors mounted directly on the axles or bogies, which convert the electricity back into mechanical rotation to drive the wheels. The diesel-electric system offers numerous advantages. It eliminates the need for large and complex gearboxes. It allows flexible control of power through electrical circuits, and it permits multiple locomotives to be coupled together and controlled from a single cab by simply linking the electrical control circuits. These locomotives are also easier to operate under heavy loads because traction motors provide excellent low-speed torque and can be adjusted independently to reduce wheel slip. The diesel-electric type has become the global standard because it combines the efficiency of diesel engines with the flexibility and controllability of electric power transmission. It is used for both freight and passenger service in nearly every major railway system around the world, from long-haul freight trains in North America to high-speed passenger services in parts of Europe and Asia. The choice between these three types has always been shaped by economic and operational needs for small-scale operations, where simplicity is valued. Diesel, mechanical locomotives remain useful for medium-duty service. In certain regions, diesel hydraulic systems have proven effective, though their global share has declined over time. For the largest and most demanding railway networks, diesel-electric locomotives dominate because of their scalability, reliability, and versatility. The history of diesel. Locomotive design is therefore not only a story of adopting diesel engines, but also a story of how engineers found different ways to transmit the power of those engines to the rails. And each solution tells us something about the priorities of the time. Whether it was cost efficiency, smoothness of power, or the ability to move the heaviest trains ever conceived. The variety of transmission systems highlights the adaptability of diesel technology and the ingenuity of the engineers who refined it for so many different contexts. A diesel locomotive may seem from the outside like a simple rectangular body resting on heavy wheels, but inside it is a carefully organized arrangement of components, each fulfilling a precise role to ensure the machine can run for thousands of hours under immense stress. The anatomy of a diesel locomotive begins with the driver's cab, usually positioned at one or both ends of the body. This space contains the throttle brake controls, gauges, indicators, switches, and in modern designs, computer screens that allow the operator to monitor and command the entire system from a single location. The cab is reinforced for safety, insulated for noise, and designed to give maximum visibility so that the driver can react to signals, curves, and conditions on the track. Immediately behind the cab lies the engine compartment, which contains the prime mover, the large diesel engine itself. This is a massive multi-cylinder unit built with heavy cast blocks, strong crankshafts, and turbochargers to increase efficiency. Connected directly to the engine is the generator or alternator, which converts the mechanical rotation into electricity used to power the traction motors. The generator is one of the most important links in the chain, because without it, the diesel engine could not be transformed into useful tractive effort surrounding the engine. Our subsystems, such as fuel filters, injectors, lubrication, pumps, and turbochargers, all of which contribute to performance alongside the engine. One finds the cooling system, because such a large engine produces enormous amounts of heat. This system includes radiators, coolant tanks, and powerful fans, usually mounted on the roof or sides that pull air through wide grills. The sound of these fans is one of the most recognizable noises of a locomotive. Below the floor of the central body sits the large fuel tank, often capable of holding several thousand liters of diesel fuel. This tank feeds the engine through pumps and filters, ensuring a steady supply, even on steep gradients or during vibration. Moving further through the locomotive, one comes to the electrical control compartment in older locomotives. This contained racks of relays, resistors, and contactors, while in modern versions, it is filled with solid-state electronics that regulate voltage, distribute power to the traction motors, and manage protective circuits. The sophistication of this electrical gear makes modern locomotives far more efficient than their predecessors. Below the main body are the bogies, also known as trucks. These massive steel frames carry the axles, suspension systems, and the traction motors, themselves in a diesel-electric locomotive. Each axle is usually powered by its own motor, which receives current from the generator through the control system. The bogies are designed to pivot, allowing the locomotive to take curves while spreading the enormous weight of the machine over multiple wheels. They also contain braking equipment, both traditional air brakes and, in many locomotives, dynamic braking, which uses the traction motors as generators to create resistance and slow the train. Additional equipment is spread throughout the locomotive, including the air compressor that supplies pressure for the braking system, the sanding gear that drops sand onto the rails for better traction, the battery bank that provides auxiliary power, the exhaust system that channels gases away from the engine, and the lighting that ensures visibility in dark tunnels or night operation. All of these systems are integrated within a strong outer shell called the car body, which not only provides protection against weather and collisions, but also adds structural strength to withstand the stresses of high-speed travel, coupling forces, and continuous vibration. Maintenance access is provided through hatches, ladders, and walkways, so that engineers can inspect, repair, and service components without dismantling the entire locomotive when considered as a whole. The anatomy of a diesel locomotive reveals a complete ecosystem of interdependent systems: fuel combustion, cooling electricity, braking, suspension, and control. Each part designed not to stand alone, but to function in harmony with the others. The result is a machine that can haul thousands of tons of freight or carry passengers at sustained speeds across vast distances, reliably and safely. And by studying this internal layout, we see the culmination of decades of engineering refinement. Every detail, from the position of the fuel tank to the placement of the cooling fans, has been determined by the need for efficiency, reliability, and ease of service. Together, these elements form one of the most impressive pieces of machinery ever created, a vehicle that embodies the essence of modern rail transport. The fuel system and combustion process are the true lifeline of every diesel locomotive, because without a steady and carefully managed supply of diesel fuel, the powerful prime mover cannot generate the energy needed to move thousands of tons of weight across rail networks. And when we examine this subject in detail, we see how every component of the system has been designed to maintain reliability, efficiency, and safety. The fuel begins its journey in the large storage tank that lies beneath the frame of the locomotive. This tank is built from heavy steel, capable of withstanding impacts and vibration, and it usually holds thousands of litres of diesel, which ensures that the locomotive can travel for long distances without interruption. Inside, the tank baffles are installed to reduce the movement of liquid when the locomotive accelerates or brakes, and venting systems control pressure as the fuel level changes. The next step in the process involves fuel pumps, which draw the liquid from the tank and push it through a network of filters. These filters are of great importance because diesel engines demand an extremely clean supply of fuel. Even a small amount of water or dirt can clog injectors or cause wear in the cylinders. So the filtration system is built with multiple layers to guarantee purity. Once the fuel has passed through this stage, it is pressurized and directed toward the engine block where the injectors are located. The fuel injectors are among the most critical components in the entire locomotive engine, because their purpose is to spray fuel directly into the combustion chamber at precisely the right moment under extremely high pressure. The atomization of the fuel into fine droplets allows it to mix thoroughly with the air that has already been compressed inside the cylinder. When the piston rises on the compression stroke, the air becomes very hot, and as soon as the fuel is injected, it ignites without the need for a spark plug. This principle of compression, ignition, is what defines the diesel cycle. The ignition generates a rapid rise in temperature and pressure that drives the piston downward, creating the power stroke, which turns the crankshaft and ultimately provides the energy to move the train. This process is repeated in every cylinder, many times per second. and the combined output creates the horsepower and torque for which diesel locomotives are famous. In order to optimize this cycle, the air supply is increased by means of turbochargers, which capture energy from the exhaust gases to spin a turbine connected to a compressor that forces extra air into the cylinders. The more oxygen available, the more complete the combustion, and the greater the efficiency of the engine. This design allows locomotives to generate enormous power without making the engine physically larger. Supporting systems play essential roles in sustaining the combustion process. The cooling system circulates coolant through channels around the cylinders and carries the heat away to radiators that are mounted on the roof or sides, where powerful fans expel it into the atmosphere. Without constant cooling, the intense heat of combustion would quickly destroy the engine. Another equally important system is lubrication. Oil is pumped under pressure throughout the engine to coat moving parts, reduce friction, and absorb heat. Without proper lubrication, the violent forces created by combustion would cause catastrophic damage within minutes. Together, cooling and lubrication ensure that the prime mover can run continuously for days at a time, while hauling heavy loads. Alongside these core systems is the exhaust arrangement, which directs gases out of the engine block through large pipes and mufflers. The exhaust often emerges from the roof, and its noise and smoke have become a symbol of diesel power. In modern locomotives, exhaust treatment systems may also reduce harmful emissions and improve environmental performance. Another essential link in the fuel chain is the control system. In older locomotives, mechanical governors adjusted fuel delivery, while in modern engines, electronic management systems constantly monitor speed load and temperature and adjust injection timing, pressure, and fuel quantity to achieve maximum efficiency and reduced emissions. This real-time control allows the locomotive to maintain smooth performance under a wide range of conditions, whether it is hauling a heavy freight train up a mountain pass or moving at steady speed across flat plains. The entire sequence of events, from fuel leaving the tank to its final combustion inside the cylinder, represents one of the most finely tuned processes in engineering. Every pump, filter, injector valve, and sensor has been placed to guarantee that the combustion can take place thousands of times per minute, with no interruptions. When viewed together, the fuel system and combustion process reveal a perfect balance between raw energy and careful precision. It is this balance that makes the diesel locomotive not only a machine of brute force, but also a marvel of controlled engineering. And by understanding it in detail, we can appreciate why these locomotives became the backbone of rail transport, providing continuous power range and reliability for generation after generation. The cooling and lubrication systems of a diesel locomotive are among the most essential support structures, without which the prime mover could not continue to function for more than a few minutes, because the forces generated by combustion are so extreme that they produce both intense heat and constant friction inside the engine block. When engineers design a locomotive, they must therefore ensure that every component can operate in harmony with systems that regulate temperature and minimize wear. The cooling system begins with a network of passages called water jackets, built directly into the cylinder block and cylinder head, through which coolant flows. This coolant is usually a mixture of water and antifreeze that circulates continuously, driven by powerful pumps. As the engine runs, the coolant absorbs the enormous heat created by combustion and carries it toward large radiators mounted on the roof or sides of the locomotive. These radiators look much like those in automobiles, but are far larger and more robust. Fans powered either mechanically or electrically force air through the radiator fins, transferring the heat from the coolant to the surrounding atmosphere. Without this continuous removal of heat, the metal components of the engine would expand, warp, and eventually fail when the locomotive is working hard on steep gradients or under heavy load. The cooling fans accelerate automatically to handle the extra heat produced by the engine, and the distinctive roar of these fans is one of the characteristic sounds of a locomotive in service. The cooling system also contains thermostats that regulate the flow of coolant, ensuring that the engine maintains an optimal operating temperature, because if it runs too cold, efficiency is reduced, and if it runs too hot, components can be destroyed. In addition, expansion tanks provide space for coolant to expand when it is heated, and filters remove impurities that might clog the system. The lubrication system is equally critical, because every moving surface within the engine, such as pistons, bearings, crankshafts, and camshafts, experiences constant mechanical stress. Oil is stored in a sump at the bottom of the engine block from where pumps draw it and send it under pressure through a network of channels and galleries that reach every critical part. The oil forms a thin, protective film between moving surfaces, preventing direct contact and drastically reducing friction. It also carries away heat and microscopic particles of wear that are then trapped in oil filters before the oil is recirculated in high performance. Locomotive engines. The lubrication system is designed for redundancy, with multiple pumps and pressure sensors to ensure a constant flow. Even if the engine is tilted on curves or experiencing vibration, without oil flow, the engine would seize in a matter of seconds, which is why alarms and automatic shutdown systems are built into modern locomotives to protect against catastrophic damage. Together, the cooling and lubrication systems allow the diesel engine to operate continuously for days at a time, hauling immense loads while maintaining a stable temperature and keeping wear under control. These systems are monitored constantly from the cab by gauges and sensors that display coolant temperature, oil pressure, and other vital parameters. And in modern locomotives, electronic control units automatically adjust fan speeds or issue warnings. If a problem is detected beyond their technical function, these systems also represent the philosophy of locomotive engineering, which is to create machines that are not only powerful, but also reliable under the most demanding conditions. Because a locomotive may be working far from maintenance depots, in remote areas, it must carry its own means of self-preservation in the form of these protective systems. The balance between heat removal and lubrication is delicate, yet robust, and it illustrates how engineering transforms raw energy into usable motion without destroying the very machine that generates it. When we consider the role of these systems together, it becomes clear that they are not secondary, but primary elements in the anatomy of a diesel locomotive. For the engine can only continue its work if it is kept within narrow limits of temperature and mechanical integrity. And by understanding how cooling and lubrication operate, we gain a deeper appreciation for the remarkable durability that has made diesel locomotives the backbone of modern rail transport. The electrical system of a diesel locomotive is the bridge between the raw mechanical energy produced by the diesel engine and the tractive power that ultimately moves the train. Because in a diesel-electric locomotive, the engine does not directly turn the wheels. Instead, it drives a generator or alternator that produces electricity, which is then distributed to traction motors mounted on the axles. This arrangement allows great flexibility and is the reason why diesel-electric technology has become the global standard. The generator sits directly coupled to the crankshaft of the diesel engine, and as the crankshaft rotates, the generator converts the rotational energy into electrical energy. In early locomotives, this generator was usually a direct current machine with brushes and commutators that sent electricity directly to the traction motors. However, as technology advanced, alternating current alternators became more common because they were more efficient, required less maintenance, and could handle higher power outputs. Modern locomotives therefore use large alternators that generate alternating current, which is then rectified into direct current or converted again into controlled alternating current, depending on the traction, motor design from the generator. The electricity flows into a system of controls and regulators in older locomotives. This system relied on banks of resistors, contactors and relays, which adjusted the current, flowing to the traction motors, depending on throttle position. In modern designs, these mechanical components have been replaced by solid-state power, electronics, including inverters, rectifiers, and microprocessor controls. These devices allow very precise management of voltage and current so that each traction motor receives the exact amount of power required for the train's speed and load conditions. Traction motors themselves are robust. Electric machines mounted directly on the axles or in the bogies, and they convert the electrical energy back into mechanical rotation, which turns the wheels. The advantage of this system is that traction motors provide very high torque at low speeds, making it possible for locomotives to start heavy trains smoothly without the need for complicated gearboxes. The electrical system also makes it possible to control multiple locomotives from a single cab through multiple unit connections, so that 2 or 3 or more locomotives can be coupled together and operate as one machine by linking their control circuits. Another feature of the electrical system is dynamic braking. When a locomotive is descending a grade or slowing down, the traction motors can be switched to act as generators instead of consuming electricity. They produce it, converting the kinetic energy of the train into electrical energy, which is then dissipated as heat through resistor grids mounted on the roof. This provides a powerful form of braking that reduces wear on mechanical brakes and improves safety, especially on long descents. In addition to traction power, the electrical system also supports auxiliary functions. Batteries provide low-voltage electricity for starting the engine running. Lights powering control circuits and operating systems when the engine is not running. Once the engine starts, the generator or alternator supplies power, not only to the traction motors, but also to these auxiliary circuits through converters and regulators. The reliability of the electrical system is critical because any failure in the generator wiring or traction motors can disable the entire locomotive. Engineers have therefore designed redundant systems, heavy insulation, cooling fans for the traction motors, and monitoring sensors that feed information back to the control system so that problems can be detected before they become catastrophic when viewed as a whole. The electrical system and generator arrangement represent a remarkable fusion of mechanical and electrical engineering, taking the steady turning of a crankshaft and converting it into controlled electric currents that drive massive steel wheels along the rails. This system has proven so effective that it has defined locomotive design for more than 70 years and continues to evolve with advances in semiconductor technology, digital controls, and improved traction. Motor designs by mastering the integration of generators, traction motors and electronic control units. Engineers created a locomotive that is not only powerful, but also flexible, scalable, and capable of meeting the demanding needs of freight and passenger rail across the world. Traction motors and the systems of power transmission in a diesel-electric locomotive are the components that transform electrical energy into the physical force that turns the wheels and propels the train forward. And when studied closely, they reveal one of the most important reasons why diesel-electric technology became dominant in global railway operations, because these motors provide immense torque control, efficiency, and durability in ways that mechanical transmissions cannot achieve. A traction motor is essentially a large electric motor mounted on the bogie of the locomotive and connected either directly or through gears to the axle that carries the wheels. In early diesel electric locomotives, these were usually direct current motors because the generators produced direct current electricity, and such motors could deliver high torque at low speeds, which was exactly what was needed for starting heavy trains. However, as alternators replaced generators, alternating current traction, motors became more common, and with the rise of advanced power electronics, alternating current motors could be controlled just as precisely while offering longer life, less maintenance, and higher efficiency. The traction motor receives electricity from the generator through a network of control circuits which regulate the voltage and current depending on throttle settings, train speed, and track conditions. When the train is at rest, the system supplies high current at low voltage to the motors, producing tremendous torque that allows the locomotive to overcome inertia and set the train in motion as speed increases. The control circuits adjust the balance, supplying higher voltage at lower current to maintain momentum efficiently. This seamless adjustment is one of the great advantages of electric transmission because it allows smooth acceleration without mechanical gear. Shifting. Traction motors are usually mounted in a way that they partially rest on the axle, but are also supported by the bogie frame. This arrangement reduces unsprung mass while still transmitting torque. Effectively, gears connect the motor armature to the axle, reducing the motor's high rotational speed to the lower speed of the wheels and multiplying torque in the process. Cooling fans are often built directly into the motor housing because the high currents generate heat that must be dissipated to prevent damage. Lubrication systems are also provided for the gears to ensure long life under heavy loads. Power transmission through traction motors provide several unique benefits compared to mechanical or hydraulic drives. First, it distributes power evenly across all powered axles so that the locomotive can use its weight for maximum adhesion to the rails. Second, it allows precise control of wheel slip because sensors can monitor the rotation of each axle and reduce power to any motor that begins to spin. This prevents damage to rails and wheels and ensures effective traction under varying conditions, such as wet tracks, snow, or heavy gradients. Third, the system enables dynamic braking when descending steep grades. The traction motors can be switched from motoring mode to generating mode, in which they resist the turning of the wheels and convert the kinetic energy of the train into electricity that is then dissipated through resistor grids mounted on the roof. This form of braking is invaluable because it reduces wear on mechanical brake shoes and provides a steady, controllable resistance that keeps long trains under control without overheating. The brakes, the combination of traction motors and power electronics, also makes it possible to operate multiple locomotives together in what is called multiple unit control, because each traction motor is managed by its own circuits and linked to the throttle in the lead cab. The driver can command several locomotives at once, allowing trains of great length and weight to be moved by coordinated power. The durability of traction. Motors is another essential feature. Because locomotives are expected to run for decades under extreme conditions, the motors are built with rugged insulation, heavy windings and sealed housings to keep out dust, moisture and debris. Maintenance teams regularly inspect brushes, bearings and insulation in older direct current designs. While alternating, current motors require less frequent attention because they have fewer wear components. The history of traction motors shows continuous evolution from early direct current machines with simple resistive controls to modern alternating current motors with sophisticated electronic inverters. Yet the principle remains unchanged, which is to convert electricity into torque at the wheels. The success of diesel-electric locomotives is largely due to this principle, because it created a flexible, scalable, and reliable means of transmitting power from the engine to the rails, and by examining traction motors and their role in power transmission, we see clearly how electrical engineering and mechanical engineering were combined to create one of the most effective transportation technologies of the modern age. The control systems and driver's cab design of a diesel locomotive represent the vital interface between the complex machinery hidden inside the body of the locomotive and the human operator who must guide it safely across vast distances. Because no matter how powerful the engine or how efficient the traction motors may be, the entire train depends on the ability of the driver to control that power with precision, reliability, and safety. The cab is the command center, a carefully designed workspace filled with levers, switches, gauges, and in modern locomotives, digital screens that provide real-time information about every major system. In the earliest diesel locomotives, the cab was relatively simple, with a throttle lever that directly adjusted the output of the engine and a brake valve that controlled the air pressure in the train's braking system. Gauges displayed basic parameters such as fuel level, oil, pressure, coolant, temperature, and speed. But as locomotives became more sophisticated and electronics advanced, the cab evolved into a far more complex environment. Today, a driver sits before an array of controls that monitor and manage not only the engine and brakes, but also the electrical systems, traction motors, cooling fans, fuel pumps, and safety devices. The throttle of a diesel locomotive is not a simple accelerator, like in an automobile, but a multi-position control lever, usually with 8 power notches, plus idle and shutdown. Each notch corresponds to a preset engine speed and power output, allowing the driver to select the exact level of power required for the conditions this system provides. Predictable and repeatable performance, which is essential when handling long freight trains or high-speed passenger services. The brake system is equally important and is usually controlled by 1 or 2 handles connected to the air brake system. One handle operates the train brakes, which apply to all cars through a system of compressed air pipes, while the other controls the independent brakes, which act only on the locomotive itself. Mastering the use of these brakes requires skill, because the momentum of a long train is enormous, and stopping distances must be carefully judged alongside the throttle and brakes. The cab contains displays for monitoring traction, motor current, wheel slip coolant, temperature, oil pressure, and fuel flow. Modern locomotives integrate these into digital screens that can display warnings and even suggest corrective actions. Electronic control units link all of the locomotive's subsystems together, and allow the driver to manage them through software interfaces instead of purely mechanical levers. Another aspect of control is safety systems. Railways across the world mandate that locomotives be equipped with devices such as deadman pedals, vigilance controls, or automatic train protection systems. These ensure that if the driver becomes incapacitated or fails to react to signals, the locomotive will slow or stop automatically. Many cabs also contain communication equipment, radios for talking to dispatchers and other trains, and event recorders, often called black boxes, that log every action of the driver and every response of the locomotive. The physical design of the cab is shaped by ergonomic and safety considerations. The driver's seat is placed to provide maximum visibility of the track ahead. Controls are arranged so they can be reached easily without distraction, and the cab is insulated against noise, heat, and vibration. In some locomotives, climate control systems are installed to maintain comfort. During long hours of operation, windows are reinforced to resist impact from debris, and lighting is arranged so that instruments are visible both in daylight and at night in dual cab locomotives. The design is mirrored so that the train can be operated in either direction without turning. The cab is therefore not just a workspace, but also a protective environment, because the driver must remain alert and effective even during shifts that may last many hours. The evolution of cab design reflects broader trends in railway technology, from mechanical simplicity to electronic complexity, from isolated operation to integrated digital networks. Yet the core purpose has remained the same, which is to give the human operator complete, reliable, and safe control over one of the most powerful machines ever built. And by studying the cab and its control systems, we see how engineering has balanced the brute force of diesel power with the delicacy of human command, creating a harmony between machine and operator that lies at the heart of modern railway transport. Safety systems in diesel locomotives are essential because they protect not only the crew operating the locomotive, but also the cargo passengers and communities through which the train passes. Since locomotives are massive machines capable of moving at high speeds while carrying thousands of tons of freight or hundreds of passengers, their operation requires multiple layers of safety technology to reduce risks and ensure predictable performance. The most basic safety feature is the braking system, which uses compressed air to apply brakes throughout the entire train. This air brake system, invented in the 19th century, has been refined for modern locomotives and is now managed by electronic valves, sensors, and control logic. The engineer can apply service brakes gradually or emergency brakes instantly. And in addition, the locomotive is equipped with independent brakes that act only on its own wheels, allowing more precise handling when shunting or coupling. The braking system is supported by dynamic braking, which uses the traction motors to generate resistance when descending long grades, reducing heat and wear on mechanical brake components. Another fundamental safety system is the deadman control, sometimes in the form of a pedal, sometimes as a spring-loaded lever that the driver must press or hold. If the driver releases the control for too long, the locomotive assumes the operator is incapacitated and applies the brakes automatically. Vigilance control systems expand on this idea by requiring periodic input from the driver, such as moving a control or pressing a button at timed intervals. If no response is detected, the system sounds alarms and eventually initiates braking. These devices ensure that the locomotive cannot continue unchecked without an alert operator. Many locomotives are also fitted with automatic train protection systems, which monitor signals and speed limits and intervene if the driver fails to act. If a signal is passed at danger, or if the train exceeds the permitted speed, the system can override the controls and apply the brakes. Modern systems, like positive train control in the United States or the European train control system, provide continuous monitoring and communication between trackside equipment and the locomotive, enforcing compliance with operating rules and greatly reducing the risk of accidents. Communication is itself a key safety system. Locomotives are equipped with radios that allow constant contact with dispatchers, other trains and maintenance staff, ensuring that any hazards or instructions are conveyed instantly. Event recorders, often called black boxes, log every control input and system response, so that in the event of an incident, investigators can reconstruct what happened and improve future safety standards. Fire detection and suppression systems are installed in engine compartments because the combination of fuel heat and electrical equipment creates a risk of fire sensors, detect smoke or excessive temperatures, and trigger alarms or release extinguishing agents automatically, protecting both crew and equipment. Modern locomotives also carry extensive sensor networks that monitor oil pressure, coolant, temperature, traction, motor, current, and wheel slip if any parameter goes outside. Safe limits. Warnings are issued, and in some cases, the system reduces power or shuts down the engine to prevent damage. Physical safety for the crew is addressed through cab design, which includes reinforced structures, crash-worthy seats, shatter-resistant windows, and climate control that prevents heat stress or fatigue. During long hours, lighting horns and bells are also considered safety systems because they warn trackside workers, motorists, and pedestrians of an approaching train. Sanders mounted on the locomotive drop sand onto the rails to increase adhesion in slippery conditions, preventing wheel slip or uncontrolled braking. Ultimately, the philosophy behind all these systems is redundancy and fail-safe design. If one system fails, another is available to intervene, and if the operator makes a mistake, automated protections reduce the consequences. The integration of mechanical, pneumatic, electrical, and electronic safeguards has turned the diesel locomotive into one of the safest heavy machines in continuous operation. And by examining these systems, we see not only how engineers protect lives, but also how they ensure that railways remain one of the most secure and reliable forms of transportation in the modern world. Maintenance and servicing of diesel engines in locomotives are critical aspects of railway operations because these massive machines are expected to operate reliably for thousands of hours under extreme loads and conditions without proper care. Even the most advanced diesel locomotive would soon fail. The goal of maintenance is to preserve efficiency, extend the lifespan of components, prevent unexpected breakdowns, and ensure safety. The process begins with routine inspections, which are performed daily or weekly, depending on usage. During these checks, crews examine fluid levels such as fuel oil and coolant, and they also look for visible leaks, loose connections, or unusual noises. Simple tasks like topping up oil or coolant, replacing filters, and cleaning air intakes may seem minor, but they prevent small issues from growing into major failures. More extensive scheduled maintenance occurs at fixed intervals, often measured in hours of operation. Locomotives are brought into service. Depots where mechanics perform systematic checks of the engine, the fuel injection system, the cooling system, and the electrical equipment. Lubricating oil is drained and replaced. Filters are changed and worn. Belts or hoses are replaced. Traction. Motors are inspected for insulation. Wear and proper functioning and diagnostic equipment may be connected to the locomotive to read error codes and performance data. This preventive maintenance is the foundation of reliability because it allows issues to be addressed before they cause breakdowns. Another major aspect of servicing is overhauling the prime mover itself over time. Pistons, rings, bearings, and valves wear out due to the immense forces inside the cylinders. An overhaul may involve removing the engine from the locomotive, disassembling it completely, and replacing or machining worn components. Such work is expensive and time-consuming, but it restores the engine to near new condition, allowing it to continue in service for many more years. Cooling systems require their own maintenance because radiators can become clogged by debris or corroded by chemicals. Coolant pumps and fans must be checked and thermostats calibrated to ensure proper regulation of engine temperature. The lubrication system is similarly monitored because oil contamination or pump failure could quickly destroy the engine. Samples of oil are often tested in laboratories to detect metal particles or chemical changes that reveal hidden wear before it becomes critical. The fuel system also demands constant attention. Injectors must be cleaned or replaced, filters swapped, and pumps tested for correct pressure because poor fuel delivery reduces efficiency and increases emissions. Modern locomotives often rely on computer systems to assist with maintenance. Electronic control units log operating data, such as engine hours, temperatures, loads, and fault codes. This data is downloaded during servicing and helps mechanics predict which parts are likely to fail soon, enabling a shift from reactive maintenance to predictive maintenance, where issues are corrected before failure occurs. Beyond the engine itself, maintenance includes the running gear, bogies, wheels, and braking systems. Wheels must be reprofiled on lathes to maintain correct shape and prevent track damage. Bearings are inspected and replaced, and brake shoes or pads are checked for wear. Air compressors are tested because a failure in the braking system would endanger the entire train safety checks, therefore form a core part of every service schedule. Locomotive servicing also considers environmental and regulatory compliance. Older locomotives may be retrofitted with upgraded exhaust systems to meet emission standards, and fuel consumption is monitored to ensure efficiency. Crews are trained to recognize early warning signs, such as smoke, color changes, vibration, or unusual gauge readings, and to report them immediately so that servicing can address problems before they worsen. Ultimately, the maintenance and servicing of diesel engines is not merely mechanical work, but a philosophy of reliability. Railways depend on locomotives that can operate day and night in harsh conditions, and only through continuous care can such performance be achieved by studying the cycles of inspection, repair, and overhaul. We see that the diesel locomotive is not just a static machine, but a living system, requiring attention and support throughout its life. And it is this dedication to maintenance that has allowed fleets of locomotives to remain in service for decades, carrying countless trains across continents without interruption. The evolution of diesel locomotive design over the decades is a story of continuous refinement in response to changing technology, economic conditions, and operational requirements. Because from their earliest appearances in the first half of the 20th century, diesel locomotives have undergone dramatic transformations in size, efficiency, control systems, and appearance. The earliest diesel locomotives built in the 1910s and 1920s were experimental units, often small and used only for shunting or short passenger services. They relied on primitive mechanical transmissions and relatively low-powered engines, but they demonstrated the potential of diesel technology to operate without the heavy infrastructure required for steam. The 1930s marked the beginning of serious development, especially in the United States and Europe, where streamlined passenger trains like the Burlington Zephyr and the German Flying Hamburger captured the imagination of the public. These early mainline diesels used diesel-electric technology, combining powerful engines with generators and traction motors to achieve reliable performance at high speeds. During this period, the visual design of locomotives also began to change from boxy, utilitarian forms to sleek, aerodynamic shapes that symbolized modernity and progress. After the Second World War, dieselization accelerated rapidly because railways needed efficient locomotives that could operate with smaller crews and lower costs. The 1940s and 1950s saw the rise of standardized designs, such as the Electromotive Division F units in North America, with their distinctive rounded noses and flexible modular construction. These locomotives became icons of post-war railroading, capable of hauling both freight and passenger trains across vast distances. In Europe, similar advances occurred with locomotives such as the British Rail Class 40 and the French CC 7100 series, reflecting the growing confidence in diesel power. The 1960s and 1970s brought further evolution with the development of high horsepower road locomotives capable of producing 3,000, 4,000, or even 5,000 horsepower advances in metallurgy, engine design, and turbocharging allowed locomotives to become more powerful without significantly increasing size. At the same time, improvements in multiple unit control and train handling enabled railroads to operate ever longer trains with fewer locomotives, reducing costs and increasing efficiency. The external design of locomotives during this era also became more angular and functional, with emphasis placed on ease of maintenance and crew visibility, rather than purely on aesthetics. The 1980s and 1990s introduced the era of microprocessor control, which revolutionized diesel locomotive design because it allowed precise monitoring and management of engine performance, traction power, and braking systems. Locomotives such as the General Electric Dash 8 series and the Electromotive SD60 series incorporated computer systems that optimized fuel consumption, reduced emissions, and extended maintenance intervals. These advances reflected broader technological changes in society as electronics became smaller, cheaper, and more reliable. By the early 21st century, diesel locomotives had evolved into highly sophisticated machines, equipped with alternating current traction, motors, inverters, and advanced diagnostic systems, allowing unprecedented levels of control and reliability. Emissions standards also began to shape locomotive design, leading to the introduction of exhaust after-treatment systems improved fuel injection technology, and enhanced cooling systems. The visual form of locomotives became more standardized with wide safety cabs in North America and streamlined monocoque designs in Europe and Asia. Yet beneath the surface, the complexity of onboard systems continued to increase. The evolution of diesel locomotive design is also a story of globalization, because manufacturers such as General Electric, Electromotive, Alstom Siemens, and others began supplying locomotives worldwide, adapting designs to local conditions, but using common technological foundations. The spread of modular construction allowed locomotives to be customized with different engines, transmissions, or safety systems, while still sharing core components. This flexibility enabled railways to meet diverse needs, from heavy freight, hauling in North America, to high-speed passenger service in Europe, and mixed traffic operations in Asia and Africa. Through all these decades, the guiding themes of diesel locomotive evolution have been efficiency, power, reliability, and adaptability. Each generation has built upon the last, producing machines that can haul more weight, use less fuel, run longer between services, and provide safer, more comfortable working conditions for crews. The history of these developments shows not only the progress of engineering, but also the ability of technology to respond to the economic and social pressures of its time, ensuring that the diesel locomotive remained central to rail transport for more than a century. Famous diesel locomotive models around the world illustrate how different countries adopted and adapted the same fundamental technology to their own needs, creating machines that became symbols of progress, industry, and national identity. One of the most iconic series is the Electromotive Division F units of the United States, introduced in the 1940s. These locomotives, with their streamlined noses and reliable diesel-electric systems, became the backbone of American railroads during the transition from steam. They were versatile, powerful, and easily recognizable. Their success established EMD as a global leader, and their design influenced generations of locomotives. That followed another famous American model is the EMD SD40, introduced in the 1960s with its 6-axle design and high horsepower. It became a workhorse for freight service across North America, known for reliability and ease of maintenance. It remained in service for decades, and many units are still operating today. General Electric also contributed legendary models such as the GE-9 series, and later the ES44 Evolution series, which pushed fuel efficiency and emissions improvements while delivering immense hauling capacity. These locomotives illustrate how the American market emphasized long-distance heavy freight operations, requiring robust, high-horsepower designs, moving to Europe. One cannot overlook the British Rail. Class 37, introduced in the early 1960s. This locomotive became a familiar sight across the United Kingdom, serving both passenger and freight trains. Its distinctive growling sound and long career made it a favourite among railway enthusiasts. Another landmark British design is the Intercity power car, officially the high-speed train introduced in the 1970s. Although technically a diesel multiple unit, its streamlined form and Paxman Valenta engines allowed speeds of 125 miles per hour, setting records for non-electrified lines and transforming Intercity travel in Britain. In Germany, diesel hydraulics reached their peak with the V200 class, introduced in the 1950s. These locomotives featured 2 engines and sleek styling, and they represented the technological pride of post-war West Germany. Another significant German locomotive is the DB Class 218, which became the standard mainline diesel locomotive across the country for decades, used in both passenger and freight service, and admired for versatility in France. The CC 72000 series deserves mention, introduced in the 1960s, with powerful engines and elegant design. These locomotives hauled express passenger services on non-electrified lines and became a symbol of modern French rail travel in the Soviet Union and later Russia. The M62 locomotive, known widely across Eastern Europe, became legendary for its ruggedness, simplicity, and ability to operate in harsh climates, built in huge numbers and exported to many Allied countries. It earned nicknames such as Tiger Drum and remains one of the most widespread diesel locomotives ever produced in India. The WDM2, built under license from Alco, became the most numerous mainline diesel locomotive type serving the Indian railways for decades. It was robust, adaptable, and capable of handling both freight and passenger services in the challenging conditions of the subcontinent. In Australia, the Clyde-built EMD locomotives, such as the NR class, became key to freight operations across vast distances where reliability and fuel efficiency are critical. In South Africa, the Class 34 locomotives, supplied by General Electric, have dominated heavy freight services, especially on mineral lines, hauling iron ore and coal over long stretches of track in Canada. The MLW and later Bombardier-built locomotives, including the M630 and M636, demonstrated Canadian adaptations of American designs to withstand extreme winter conditions. While in South America, locomotives from both North American and European builders found new life on long mountainous routes in Brazil and Argentina. The diversity of famous diesel locomotive models around the world shows how a single concept, the diesel engine driving a transmission system, could be interpreted in countless ways to meet local needs, whether it was high-speed, passenger service, rugged freight, haulage, or mixed traffic duties. Each model reflected the engineering priorities of its builders and the operational challenges of its environment. Together, they form a gallery of machines that not only carried goods and people, but also carried the identity of nations into the modern age. And their fame endures not only in continued service, but also in museums, literature, and the collective memory of rail enthusiasts worldwide. The environmental impact and efficiency of diesel locomotives are topics that have grown increasingly important over the decades, because while diesel technology revolutionized rail transport by replacing steam with a more efficient and reliable power source, it also introduced new concerns about emissions, fuel consumption, and long-term sustainability. In the early years of dieselization, environmental considerations were secondary to efficiency and cost savings compared to steam locomotives. Diesel locomotives were immediately seen as cleaner because they did not produce the vast clouds of smoke, soot, and ash that characterize steam operations. They also did not require water stops or the disposal of cinders, which reduced the strain on infrastructure and urban environments. However, as global awareness of air quality and climate change increased, attention turned toward the pollutants produced by burning diesel fuel. Diesel exhaust contains nitrogen oxides, particulates, hydrocarbons, and carbon dioxide, all of which contribute to environmental problems, from smog and acid rain to greenhouse gas accumulation. Particulate matter, in particular, has been linked to respiratory issues, while nitrogen oxides are major contributors to air pollution in populated areas. Despite these concerns, diesel locomotives have long been praised for their efficiency especially when compared to road vehicles. A single locomotive can haul thousands of tons of freight, or hundreds of passengers, using far less fuel per ton kilometre than trucks or buses. This efficiency makes rail transport one of the most environmentally friendly modes of land transport available, aside from electrified rail, because the energy cost per unit of cargo or per passenger is so low. Many studies have shown that even with emissions, diesel railways produce less environmental impact per ton mile than highway alternatives. Engineers and manufacturers have also worked continually to improve the efficiency of diesel locomotives. Advances in fuel injection systems, turbocharging, and engine management have increased the energy extracted from each litre of fuel, reducing both operating costs and emissions. In the late 20th and early 21st centuries, stricter regulations were introduced in North America, Europe, and Asia, requiring locomotives to meet emission standards similar to those imposed on trucks and industrial engines. This led to the development of new technologies, such as exhaust gas, recirculation, selective, catalytic reduction, and particulate filters, which significantly reduced nitrogen oxide and particulate emissions. Modern locomotives built to these standards are far cleaner than those of previous generations. Another aspect of environmental efficiency is fuel management. Railways have introduced driver advisory systems and automated control technologies that optimize throttle use, braking, and speed to minimize unnecessary fuel consumption by coordinating train handling with track profiles, gradients, and schedules. These systems reduce both emissions and costs. Idling. Reduction technologies have also been deployed because locomotives traditionally spent long hours idling in yards, wasting fuel and producing emissions. Today, automatic start, stop systems shut engines down when they are not needed and restart them when power or heating is required. Beyond improvements in individual locomotives, railways are also exploring the integration of alternative fuels and hybrid technologies. Biodiesel blends, liquefied natural gas, and even hydrogen are being tested as partial or complete replacements for conventional diesel fuel. Hybrid locomotives, which combine diesel engines with battery storage, are another approach, allowing energy to be recovered during braking and reused during acceleration, reducing overall fuel consumption. These innovations reflect the growing pressure on the rail industry to maintain its environmental advantage over other modes of transport while addressing the challenges of climate change. The efficiency of diesel locomotives must therefore be seen in two ways. First, as a relative measure against steam and road transport, where diesel has been a major improvement, and second, as an evolving standard, where continuous innovation seeks to reduce emissions further and improve sustainability. In summary, diesel locomotives transformed railways by providing a cleaner, more efficient alternative to steam, and by enabling rail to maintain a major environmental advantage over trucks and cars. But they also introduced new challenges that are being addressed through stricter regulations, advanced technologies, and experiments with alternative fuels. Their environmental impact is real, yet their efficiency remains undeniable. And by balancing these two aspects, we understand why diesel locomotives have remained vital for so long, and why their role in the future will depend on continued innovation and adaptation. The future of diesel locomotives in modern rail transport is a subject shaped by the balance between tradition, innovation, environmental responsibility, and economic necessity. Because while diesel locomotives have served as the backbone of global railway systems for nearly a century, the 21st century brings new pressures and opportunities. that will determine how long they continue to play a central role. On the one hand, diesel locomotives remain indispensable in many parts of the world where electrification of railways is not practical. The construction and maintenance of electrified lines with overhead wires or third rails requires immense investment, and in regions with vast networks, rugged terrain, or relatively low traffic density, diesel locomotives remain the most flexible and cost-effective solution. They can operate independently of external power supplies, travel across borders without concern for electrical standards, and provide reliable service in areas where infrastructure is limited or inconsistent. This independence ensures that for freight corridors in North America, mining routes in Australia, or long-distance services in Africa and Asia, diesel locomotives will continue to dominate for years to come. On the other hand, the environmental challenges posed by climate change are forcing the rail industry to reconsider its reliance on fossil fuels. Regulators in Europe, North America, and parts of Asia have already introduced strict emission standards for new locomotives, and similar measures are expected to spread further around the globe. Manufacturers are therefore working to redesign diesel technology to comply with these standards through the use of advanced exhaust treatment systems, improved fuel injection technologies, and electronic engine management. The result is that the newest generations of diesel locomotives are cleaner, more fuel efficient, and more environmentally acceptable than those of the past. Yet it is also clear that longer-term solutions may eventually move beyond conventional diesel power. One of the most promising developments is the use of hybrid locomotives, which combine diesel engines with battery systems. These designs allow locomotives to shut down the diesel engine when full power is not needed, drawing instead on stored electrical energy and recharging the batteries through regenerative braking. This approach reduces fuel consumption, lowers emissions, and provides flexibility, especially in yards or urban areas where quiet and clean operation is a priority. Another avenue of exploration is the use of alternative fuels, such as biodiesel, liquefied natural gas, and even hydrogen. Biodiesel can be used in existing engines with minimal modifications and offers a renewable option, though it raises questions about supply and land use. Natural gas. Locomotives have been tested in both North America and Russia, offering lower emissions, but requiring specialized fuel storage. Hydrogen-powered locomotives are also being developed, either through direct combustion in modified diesel engines, or through fuel cells that generate electricity to drive traction motors. These technologies are still in early stages, but they reflect the wider search for sustainable alternatives to conventional diesel, beyond fuels and hybrids. Digital technology is reshaping the future of diesel locomotives. Modern units are increasingly equipped with computer systems that optimize throttle use, braking, and train handling in real time, reducing both fuel consumption and wear predictive maintenance, enabled by sensors and data analysis, ensures that locomotives spend less time in workshops and more time in service, increasing their efficiency. Railways are also experimenting with remote operation and semi-autonomous systems that allow diesel locomotives to be controlled from centralized hubs, improving safety and reducing labor costs. All these changes suggest that diesel locomotives of the future will not disappear quickly, but will instead evolve into more efficient, cleaner, and smarter machines. Even in regions where electrification expands, diesel locomotives will likely remain as backup or on secondary lines where electrification is uneconomical. In this sense, the future of diesel locomotives is one of adaptation, not extinction. They will coexist with electric high-speed rail and emerging technologies, serving niches where their independence and flexibility are irreplaceable. And as engineers continue to refine their design, the diesel locomotive will maintain its place as one of the most resilient and adaptable machines in the history of rail transport, proving once again that engineering is not only about invention, but also about the continual reinvention of existing technologies to meet the needs of a changing world.